I think it's both. I think it is unquestionably true that so we can take a step backwards. At the base of all AI progress that has happened, at least in all of deep learning and arguably more, is the ability of neural networks to generalize. Now, generalization is a technical term, which means that you understand something correctly or take the right action in a situation that's unlike any situations that you've seen in the past in your experience. And you can see, and so now a system generalizes better if from the same data, it can do the right thing or understand the right situation in a broader set of situations. And so to make an analogy, suppose you have a student at a university studying for an exam. That student might say, this is a very important exam for me. Let me memorize this. Let me make sure I can solve every single exercise in the textbook. Such a student will be very well prepared and could achieve a very, very high grade in the exam. Now consider a different student who might say, you know what, I don't need to know how to solve all the exercises in the textbooks as long as I got the fundamentals right. I read the first 20 pages and I feel I got the fundamentals. If that second student also achieves a high grade in the exam, that second student did something harder than the first student. That second student exhibited a greater degree of generalization. They were able to, even though the questions were the same, the situation was less familiar for the second student than the first student. And so our neural networks are a lot like the first students. They have an incredible ability to generalize for a computer, but we could do more. And because their generalization is not yet perfect, definitely not yet at a human level, we need to compensate for it by training on very large amounts of data. That's where the data comes in. The better you generalize, the less data you need, / the further you can go with the same data. So maybe once we figure out how to make our neural networks generalize a lot better, then all those small domains, we don't have a lot of data, it actually won't matter. The neural network will say, it's okay. I know what to do well enough, even with this limited amount of data. But today, we need a lot of data. But now, when it comes to the creative applications in particular, there is some way in which they are especially well suited for neural networks. And that's because generative models play a very central role in machine learning. And the nature of the generations of generative models are somehow analogous to the artistic process. It's not perfect. It doesn't capture everything. And there is certain kinds of art which our models cannot do yet. But I think this second connection, the generative aspect of art and the ability of generative models to generate new plausible data is another reason why we've seen so much progress in generative art.
So, yeah, I mean, it's a really interesting thing, right? Because it's almost, it's a shade of what you had mentioned at the very beginning, which is that part of the reason that that maybe we shied away from neural networks at the start was that they're so hard to explain, and that aspect where we can't prove theorems about them, they do things that we can't quite explain, maybe is what naturally allows them to be better suited for creative pursuits, which we also can't explain very well.
Yeah, I think that's definitely possible as well.
Yeah. So, one thing I'm really, some of the other recent advancements from OpenAI were Clip and DALL-E, both super interesting examples of, being able to go between modalities from text to images. Maybe I would love to understand from you, what do you think is the kind of significance of sort of what is shown by Clip and DALL-E? Where do you think that research goes over time, and what excites you about it?
Yeah, so for context, so Clip and DALL-E are neural networks that learn to associate text with images. So DALL-E associates text with images in the generative direction. And Clip associates text with images, but in the direction of perception, from going from an image to text versus going from text to image. And both of them are cool because they are simple. It's the same old recipe. You just say, hey, let's take a neural net that we understand really well and just train it on a big collection of texts and image pairs and see what happens. And what happens is something very good. The real motivation with Clip and DALL-E was just to dip our toes into ways of combining the two modalities, because one of the things that we'll want in the future, I think it's fairly likely that we wouldn't want a neural nets we wouldn't want our future AIs to be text-only AIs. Like, we could, but it seems like it's a missed opportunity. I feel like so much stuff is going on in the visual world, and if it's not difficult to have a neural net really understand the visual world, then why not? And then also, hopefully, by connecting the textual world to the visual world, they will understand text better. They will have a much the understanding of text that they will learn by also being trained on images may become a little bit closer to ours. Because you could make an argument that maybe there is a distinction between what people learn and what our artificial neural networks learn. Because people see and they walk around, they do all those different things. Whereas our neural networks, the text ones are only trained on text. So maybe that means that something is missing. And maybe if you bring the training data to be more similar to that of people, then maybe we'll learn something more similar to that of people as well. So those were some of the motivations to study these models. And it was also fun to see that they worked quite well. And especially now with, I would say most recently, Clip has been enjoying quite some degree of popularity, and people have figured out how to invert it to generate high resolution images and have a lot of fun with it. And actually, I think that's the most, for me, emotionally satisfying application of the past maybe few months.
Yeah. No. Well, I think one of the I think that it's an interesting point that you mentioned, which is, hey, the more that we can, there's this concept of embodied AI, right? Which is like, hey, if you have an AI that actually will go and experience things like humans do, maybe you get the ability to do, you get interesting behaviors. And the more we can go in that direction with stuff like multimodal learning is super interesting. Another thing I wanted to touch on is, I think you mentioned something quite profound, which is, hey, they're very simple. The use of the algorithm is very simple, and in this case, producing the data sets and getting the data right is, from my perspective, what really enabled a lot of the incredible results. I don't know how you think about that and how you think that defines future similar areas of research.
I'd say it's definitely a true statement that the field of deep learning, especially the academic branch, not so much the applied branch, but the academic branch of the field has underestimated the importance of data because of the mental framework of the data is given to you in the form of a benchmark, and your goal is to create a better method that does better than the other existing methods. And the reason it was important for that framework to have a fixed data set is so that you could compare which method is better. And I think that really did lead to a blind spot where very many researchers were working very hard on this pretty difficult area of, can we improve the model more and more and more, while leaving the very large improvements that are possible by simply saying, hey, let's get much more data on the table. I think now at this point, people appreciate the importance of data a lot more. And I think that at this point, it's quite proven that domains with a lot of data will experience a lot of progress.
Do you think that more, just conceptually, do you think that over the next few years, more of the advancements, more of the cool things that we'll see in AI will come from sort of innovating more on the data side or innovating more on the algorithm side?
I prefer to not make that distinction. I think making that distinction is, it's useful for some things, and maybe let me roll with that distinction. I think both will be important. I expect us to, I believe very firmly that very huge progress is possible from algorithmic, from methodological improvements. We are nowhere yet to being as efficient as we can be with our compute. We have a lot of compute. We know how to make use of it in some way. which is already a huge achievement compared to before. Here's a historical analogy. You may remember that 10 years ago or so, the only way to productively use huge amounts of compute was through these embarrassingly parallel computations, like MapReduce. That was literally the only idea anyone had. There weren't any interesting ways in which you could use huge amounts of compute. Now with deep learning, we have one such way. You say the compute needs to be a little bit more interconnected, but it is possible to have a large amount of compute and do something useful with it. But I don't think that we have figured out the best formula for making use of this compute. I believe that there will be better formulas, and we'll be able to go much further with the same amount of compute. That said, I am also very, very confident that a lot of progress will happen from data. I mean, I'm a big believer in data, and I think that there can be so many different things. You could find new sources of data, and you can filter it in all kinds of ways, and maybe apply some machine learning to improve it. There can be I think there are lots of opportunities there. And I expect the combination of all of these when they come together, they feed off each other. And I think that will lead to the most progress.
Yeah. And one question, because to go back to this question of compute, you somewhat answered it, which is like, hey, we're going to have significantly more efficient algorithms. But if you kind of take this sort of the concept of scaling to the limit that we mentioned before, which is like, hey, if you scale everything to the limit, you'll get great performance. At some point, you're building supercomputers that are, just far too, they're way too big or they're way too expensive or whatnot to be practically feasible. How do you think as a field we get around that by getting way better at using our compute, or do you think there is some like fundamental limit of compute that like we need to kind of think about when we think about scaling laws?
So there probably does exist an ultimate way of using the compute. I don't think we found that way yet. I think we can improve the efficiency of our methods, the usefulness they derive from our compute, the extent to which they generalize. I think there are lots of opportunities that we haven't explored yet. I also agree with you that there will be physical limits and economic limits to the size of computers that one could build. And I think that progress will consist on pushing on all these axes. Now, one other thing I want to mention is that there is a huge amount of incentive to find these better methods. Like, think about what happens if you can find a method that somehow allows you to train the same neural net with half the compute. It's huge. It's like you double the size of your compute. So the amount of research there will only keep on increasing. And I believe that it will lead to success. It will take some time, perhaps, but I'm sure we'll find really, really powerful ways of training our neural nets and setting them up in far more efficient ways, far more powerful ways than what we have right now. And then, of course, we want to give those better ways all the compute it deserves and all the data it deserves.
Totally. Well, one interesting concept just kind of related to this that I'm curious to get your thoughts on. One thing that I think we've talked a little bit about before, one of the concepts of neural networks embedded in the name is that, hey, you basically have this very simple model of a neuron, and that simple model of a neuron is then allowing you to perform these like brain-like algorithms. And the reality is that neurons are actually very weird. They're very hard. There's like a lot of behaviors that we don't even fully understand mathematically, and we only have like weak empiricals to understand. And so what do you think the likelihood that our current model of neurons, which are these simple sort of like ReLU functions, are the path to produce something that will resemble a brain or things that resemble neurons? Or what do you think the chances that hey, we're on kind of this interesting but slightly wrong path with how we're designing these networks?
So my view is that it is extremely unlikely that there is anything wrong with the current neurons. I think that they might not be the best neurons, perhaps, but even if we didn't change them, we'll be able to go as far as we need to go. Now, there is still an important caveat here, which is, how do you know how many neurons you need to reach human-level intelligence? Well, you can say maybe we can look at the size of the brain. But it may be that each biological neuron is like a small supercomputer, which is built out of 1 million artificial neurons. So maybe you will need to have 1 million times more artificial neurons in your artificial neural net to be able to match the brain. That's a possibility. I don't think it will happen. I don't think it will be that bad. But I would say worst case, that would be the meaning of it. In other words, you'll need a lot more artificial neurons, for each biological neuron, for it to be possible for them to simulate the biological neurons.
Yeah. Yeah, no, it's a very interesting. It's one of these interesting questions around, how much do we try to emulate biology, or are we implicitly emulating biology by having these small neurons that then create, these like super neurons that behave strangely?
Yeah, it's not. I wouldn't even say that we are trying to emulate biology, but we are trying to be appropriately inspired by it in the right way. Emulating biology precisely, I think that would be challenging and unwise, but kind of using it as ballpark estimates, I think, can be quite productive.
Yeah. One interesting thing that, it's so funny, there's just like thing after thing after thing that OpenAI has worked on recently that's been interesting. But the Instruct series of models, I think was interesting in that it kind of, it demonstrates a potentially an interesting paradigm for how humans and models will collaborate in the future. What do you sort of, why did you guys work on the Instruct series? Why is it interesting, and what excites you about it?
Yeah, so the Instruct models are really important models. I should explain what they are and what the thinking there was. So after we trained GPT-3, we started to experiment with it and try to understand what it can do. And we found that it can do a lot of different things, but and it has a real degree of language understanding, but it's very, very not human-like. It absolutely doesn't do what you ask it to, even if it can. And so one of the problems that we've been thinking about a lot is alignment, which is, if you have a very powerful AI system, how do you make it so that it will faithfully fulfill your intent, faithfully and correctly? And the more powerful the AI system is, the greater its generalization and reasoning ability and creativity, the more important the alignment of the system becomes. Now, GPT-3 is a useful system. It's not profoundly smart, but it is already interesting. And then we can ask the simpler question of how to align GPT-3, how to build a version of GPT-3 such that it will try to the best of its abilities, as faithfully as possible, to do what you ask it to do. And so that led to the creation of the Instruct models. And it's basically a version of GPT where you just say, hey, do X, please do Y, I want Z, and it will do it. And it's super convenient, and people who use this model love it. And I think it's a great example where the more aligned model is also the more useful one.
I want to, thinking about GPT-3 and large language models, I'd be remiss to say, to not talk about sort of some of the challenges that are associated with them. In particular, GPT-3 is trained on, and the future GPTs are trained on just huge amounts of data. And there's a lot of engineering involved in like, okay, how do you like engineer this data to be to work super well? What do you think are some of the challenges, especially as we try to figure out ways to use more and more data into these machine learning systems? How do you deal with the fact that, in any sea of large data, there's going to be weird biases or weird qualities that might be tough to sift through and manage?
Yeah, lots of facets to this question. So this is something that we've been thinking about at OpenAI for a long time. Just even before training GPT-3, we've anticipated that those issues will come up, and there are challenges. I can mention some of the strategies that we've pursued to address them, and some of the ideas that we are working on to address those issues even further. So it is indeed the case that GPT-3 in particular, and models like it, they learn from the internet, and they learn the full range of data that's expressed on the internet. Now, the model isn't, and so, okay, to a first approximation, we knew that this would be an issue. And one of the advantages of releasing a model through an API is that it makes it possible to deal with such challenges around misuse or around us noticing that the model is producing undesirable outputs. Now, of course, there's a very difficult challenge of defining what that means.
Yeah, I mean, to your point, it's like there's certainly, it is a fact of life that these large data sets are going to contain some sort of chaos, noise, things that we may not, maybe from a moral perspective, you may not want to put in front of a model. But I think what you're going towards is like just from a pragmatic engineering perspective, it's going to be impossible to be precious about the data we put into the algorithm. And so let's acknowledge that that's going to happen, and then be precious about defining the performance of the algorithm post-training on it, and making sure that you're able to sort of mold the algorithm to perform in a way that you would like.
So I think that is the more productive approach long term. However, I think it is possible to be precious about the data as well, because you can take the same models and filter the data or classify it and decide what data you want to train on. And I expect that as people train these models, and as we train these models, we are experimenting with these different approaches and find the most practical and efficient way of having the model be as reasonably behaved as possible.
Yeah. No, I think the results in fine-tuning the algorithms are pretty exciting, right? Because it just means that there's more degrees of freedom to be able to produce algorithms behave in the ways that you want.
That's right. And this is a property of models that are better. So this is a counterintuitive thing. The weaker the model is, the less good your language model is, the harder it is to control. Whereas the bigger it is, the better it is, the faster it is to fine-tune, the more responsive it is to prompts which specify, one kind of behavior versus another. So in a sense, I expect that at least this flavor of the problem that we just discussed will become easier as the models become more powerful and more accurate.
Yeah. So, we weave through a bunch of very interesting topics. I want to take a chance to kind of zoom out. We started this talk by talking about how, originally when you started working on neural networks, the optimistic version was, hey, the field is going to pay attention to neural networks. And obviously now we believe more in something that resembles AGI as like the optimistic version of what the field can accomplish. I think that if we kind of, in the zoomed in approach, the past few years have just been this sort of like incredible period of new breakthroughs, very new interesting things as a result of AI. When we kind of like zoom out to maybe to a longer time horizon, what are the advancements of AI that you think are sort of, I shouldn't say on the horizon, but are just around the corner, and the ones that you think are going to have very meaningful implications for how the world will operate?
So I think that of the advances that are around the corner, I think that simple business as usual of the kind of mundane progress that we've seen over the past few years will continue. And I expect our language models, our vision models, our image generation, code, text-to-speech, speech-to-text, I expect all of them will improve across the board, and I think they'll all be impactful. And I would say with these generative models in particular, it is a little harder to reason about what kind of applications become possible once you have a better code model or a better language model, because it's not just better at one thing. It develops qualitatively new capabilities, and it unlocks qualitatively new applications. And I think there's going to be just a lot of them. I think that like deep learning will continue to grow and to expand, and I think that more and more there'll be a lot more deep learning data centers, and I think we'll have lots of interesting neural networks trained on all kinds of tasks. I think medicine, biology, by the way, I think those ones will be quite exciting. Like I read that right now, the field of biology is undergoing a revolution in terms of their ability to get data. I mean, I'm not an expert, but I think it's at least not false what I'm saying. So I think training neural networks there will be quite amazing. I think it will be interesting to see what kind of breakthroughs in medicine will lead to it. Or I should mention AlphaFold, I think is also an example there. So I think the progress is going to be stunning.
To kind of close, I mean, we have an incredible AI community that's with us today, and is probably very excited to figure out how they can ensure that AI sort of has a positive future, that we have a positive AI future. What do you think are the things that sort of everyone in the audience can take away from this conversation and work on that will help ensure that we have a positive future with AI?
So I think there are many things which are worth thinking about. I'd say the biggest one is probably to keep in mind that AI is a very powerful technology, and that it can have all kinds of applications, and to work on applications that are exciting and that are solving real problems that are the kind of applications that improve people's lives. Work on those as much as possible. And also work on methods that try to address the problems that exist with the technology to the extent they do. And that would mean some of the questions about bias and desirable outputs, and possible other questions around alignment and questions that we haven't even discussed in this conversation. So I'd say those two things. Work on useful applications, and also, whenever possible, work on reducing the harms, the real harms, and work on alignment.
Awesome. Well, thank you so much. But I would be remiss to say to not thank OpenAI and the organization for all of the incredible contributions to the field of AI over the past many years. And thank you so much again for sitting down with us.
Thank you for the conversation. I really enjoyed it.